Greetings, everybody. For today's lesson, I would like to discuss the details of the periodic table and how we represent atoms in a variety of ways, which includes the Bohr-Rutherford model and the Lewis dot diagrams in more detail. Then we will be discussing how chemical bonding happens through ionic and covalent structures. So here we have our periodic table of the elements. This is a handy website, ptable.com. And as you can see, based on the lessons and the readings you've been going through so far, that we have elements situated into metals and nonmetals, as well as metalloids. So over here, the zigzag staircase, where boron starts from, indicates to us that there are some elements on the periodic table that have both metal and nonmetal-like properties. Hydrogen is the only nonmetal that sits above group 1, whereas everything else here, starting from lithium, going across to beryllium, and so on and so forth, are the metals. What I like about this website is it gives everything in color, and you can see all of the various groups and the names of each group. And I'm going to post an alternative activity to get you more familiar with the properties of these various metal and non-metal compounds. So here we have our metals. These are the alkali metals, followed by group 2, our alkaline earth metals. We've got the transition metals or the transition elements in the center of the table. There's quite a bunch of them here. We also have the metalloids, as I mentioned, starting with the boron group and then going down the zigzag pattern here. And then we have other nonmetals, starting with carbon, nitrogen, oxygen, fluorine, etc. in this green space here. And then finally rounding out group 18 with our noble gases. So in the case of walking us through the periodic table, you will also notice that there are certain elements that exist as solid, liquid, gas, or even at an unknown substance, right? So these are the states that matter can be in when we talk about things like the physical or the chemical properties of a substance. And this will come in handy when we look at chemical bonding and reactions as well. Taking your mouse and going over a certain element, for instance, so if we take a look at iron, you can see that once we take a look at a certain element on the periodic table, inside the box gives us particular pieces of information, right? So over here is a legend to this periodic table, right? We're told something about the atomic number. We also know the symbol, the name of the compound or element in this case, and the atomic weight or atomic mass. And different periodic tables will tell us different things, right? So keep that in mind. Likewise, if we are taking a look at certain groups of elements, right? So here we have highlighted the transition metals. What's interesting about the transition metals is that they can have more than one charge. So this comes in handy when we're going to look at bonding later on and writing down chemical compounds, right? Something like iron will have different charges versus something like copper, for example, that could be a +1 charge or a +2 charge. And I'll explain the process of how we come about knowing which one to use in what situation. We also have these two groups, which are found below the periodic table. We have the lanthanoids and the actinoids. So these two series of metals have slightly various characteristics given their chemical and physical properties. So we find them along the bottom, but they do fall into period 6 and 7 as you go from left to right across the periodic table, starting from number 57 to 71 and 89 to 103. So bear in mind that you will find these other elements at the bottom of the periodic table. So how do we represent various elements? So in your reading about the atom, remember that atoms will be made up of subatomic particles. And these subatomic particles are what we call the electron. Oops. Let me see why that keeps on doing that. Let's try that again. So we've got, let's get back our pen here. We've got electrons. Those are the subatomic particles with a negative charge. We've got our protons with positive charges. Don't know why the pen doesn't want to cooperate today. Let's try that again. Just zoom out of it. And we also have our neutrons. And again, that dialog box. Sorry, this is a new whiteboard I'm trying out. Okay, now in the case of these various subatomic particles, remember that it's the protons and the neutrons that will be found in the nucleus. All right, let's try this again. It will be found in the nucleus of the atom, right? So that's in the center. Always something going on with technology here. Anyways, I think you get the idea. Right? Whereas these electrons are what will be orbiting around the nucleus. So various videos that you've seen so far would have explained this to you already, right? So the electrons orbit, right? So these are the ones found around the outside. Now, two different representations are involved in showing what atoms and elements look like, right? The protons and the neutrons will stick together to form the center of the atom. The electrons orbit or circle around the nucleus, but too quickly to point their exact locations, right? So when the electrons are moving about, they're moving about very quickly. But the electrons are those subatomic particles, which we will look at in more detail when we discuss, okay, well, is something undergoing an ionic bond versus a covalent bond. So there's something what we call electron transfer versus electron sharing. So let's take a closer look at how we can represent these in more detail. So I'm just going to erase our page here, and so we can start again. So let's say that we are looking at the element carbon. So carbon on periodic table is element number, well, I'll let you look that up. Or we can go to our periodic table briefly before I write down any pieces of information here. So if we just switch over to P table, so you know how to use your periodic table, that's element number 6, right? So you can see over, if we just bring up some information and it opens Wikipedia for us, right? Carbon is known as graphite, diamond, so it has various forms, and it says that it has the symbol C and its atomic number 6, right? It's a non-metallic tetravalent element making 4 electrons available to form covalent chemical bonds, right? So it gives us a little bit of information there, and you could read up further to find out where carbon is found on Earth, etc. So in any case, what we want to know is what is the atomic number of carbon And what is the atomic mass of carbon, so that we can write down the chemical or nuclear notation for this element. So let's go back to our whiteboard and jot this information down. So carbon, we know, is symbol C. Right? And we know that for any element X, it will have an atomic mass and an atomic number, right? So in that form A and Z, just like what I had previously shown you in one of our tutorials. So just so we have more room. So if we're talking about carbon as being element 6, we're going to write the atomic number at the bottom. So kind of like a subscript to the chemical symbol, which is C from the periodic table, and the atomic mass will be written above. So this tells us some pieces of information. So we know that the atomic number is 6. So I'm just going to say that this is the atomic number. Right, so that's our atomic number. And then we know that the atomic mass number, or we'll just say the mass number, is 12. So this is how much atomic mass units carbon has. And that number 12 is going to become handy to us once we get into the math component in Unit 2. So this is how we would do chemical notation for carbon. Now, let's say we wanted to write the chemical notation for, I don't know, neon. So over here on this side, just for some extra practice, let's write down some chemical notation for neon. So we are going to go back to the periodic table and look for neon. Okay, so looking over, group 1, is neon over there? No. Group 2, is neon over there? No. Maybe it's over here on the right-hand side, right? So let's look. We had carbon over here, number 6. You're going to read the full name of the element in order to identify, right? Keep on going, fluorine. Oh, there we go. Element number 10 is neon, and the chemical symbol is Ne. So we're going to write that down on our whiteboard. So remember in your mind, Ne, 10, and also we need to know what the atomic mass is, right? So that's 20. So we need to remember 3 things. We need to remember, so I'll just circle that for you. We need to remember that we have 10. We need to remember this chemical symbol, and we need to also remember the mass is 20. So we will now rewrite that in the correct format on our whiteboard. So how do we depict the neon? Well, we're going to write Ne, and then what was the number for the element or the atomic number? That was 10. So the 10 goes down here. And the atomic mass number was 20. So the larger number goes at the top. The smaller number goes at the bottom. So that's an easy way or an easy trick for you to remember. Now, what else can we learn from these numbers? So chemical notation helps us to draw the Bohr-Rutherford model for the atom. So those are those diagrams where you'll see the number of protons and number of neutrons written in the center or in the middle of the diagram. And then you'll see little dots orbiting in circles around the nucleus. So how do you figure out your number of protons, number of neutrons, number of electrons, all that stuff? Well, again, that comes from our chemical notation. So, easy way to figure that out. Remember that your number of protons and number of electrons are the same as your atomic number. Okay? So, we're going to note that down. So, your number of protons and electrons are the same as your atomic number. So in the case of neon, if neon's atomic number over here is 10, that means that neon has 10 protons and 10 electrons. Now, how do you figure out how many neutrons something has? Well, the neutrons are going to be related to the atomic mass. So the number of neutrons can be found by taking your atomic mass and subtracting it from the atomic number. So it's basically saying that 20 minus 10 equals your number of neutrons. Oops, that looks like a 6. Let's fix that, or maybe I should rewrite what I just mentioned to you. So if you want to know your number of neutrons, we'll put that little number sign here. So your number of neutrons is equal to your mass number subtracted from your atomic number. So in the case of neon, that would be 20 minus 10. Right? Hopefully we can all do 20 subtract 10 in our head to give us 10 neutrons. Right? If you wanted to do that for carbon, same idea. You'll just do 12 minus 6, and hopefully you figured out that carbon has 6 neutrons. Now, what you're going to notice is that with all of these numbers as well, and if you correspond the numbers that we used for chemical notation to the periodic table, I kind of didn't use the decimals. So what you want to keep in mind is that we're always rounding to the nearest whole number. So going back to our periodic table quickly, and then we'll move on to Bohr-Rutherford models and Lewis dot diagrams, right? You'll notice over here, oxygen, for example, has element number 8, right? So this is the atomic number for oxygen, but it has a mass number of 15.999. Now, what you would do is here, you wouldn't write down the atomic mass as 15.9. Instead, you could just round up to 16. And then you just do the math, figure out your number of neutrons, right? Same thing for something like cobalt, right? Cobalt is atomic number 27. It has an atomic mass of 58.9. Again, just round up to the nearest whole number. Therefore, you would use number 59. Okay, so I'm going to post some practice information. So I'll post some tables that you can fill out to figure out an element's number of electrons, number of protons, number of neutrons, the chemical symbol, how to write this stuff down in proper chemical notation, things like that, and another exercise in working with the periodic table, which is slightly different to the coloring activity you did to identify the metals, the non-metals, and noble gases, and the different groups and things like that. Now, moving on, we are going to take a look at the Bohr-Rutherford model of the atom, as well as talking about Lewis dot diagrams. So I'm going to bring up two images here. So first we're going to look at the Lewis dot diagrams, also known as Lewis structures. So we'll bring this one up in more detail. So I'm just going to copy this image and open a new whiteboard. So those are the Lewis dot diagrams. And I'm going to pick an element of focus off of here. So we'll just use carbon again. And I'm going to also find an image for you of carbon's Bohr-Rutherford model. Since it will take us way too long, whoops, to draw all of that out. Yeah, this looks good. So let's use that one. Okay. So two very interesting depictions of the atom. So what's different about each of these particular representations is that the Bohr-Rutherford model, you will notice, shows you all of the electrons that an element has, so the total number of electrons, whereas the Lewis dot diagrams, or the Lewis structures that we see over here on the right-hand side, are only showing you the elements in the outermost valence level of the electron. So for example, for that element carbon, right, you're going to see, we'll open up the highlighter here, that we have, now I'll use a orange color, 4 electrons here. So there's 1, 2, 3, 4 electrons in this outermost orbit, right? So in that second energy level, or energy shell as they call it for the carbon. Likewise, for this Lewis dot structure, there's only 4 dots. 1, 2, 3, 4. So those 4 dots correspond to the last 4 electrons that will be participating in a chemical bond. Whether that's ionic or covalent will depend on the nature of the carbon atom. The other 2 electrons, which are found here, right, closer to the nucleus, right, those make up the total number of electrons, right? And remember, I told you previously that your atomic number for an element is equal to the total number of protons and number of electrons for that specified element under focus, right? Here in the green, we have the nucleus, which contains the protons and the neutrons together. Electrons orbit around the nucleus on the outside in these various energy levels. And if you're trying to figure out how many electrons to put in each shell, basically what happens is that in the first shell, you have 2 electrons. In the second shell, we can get up to a maximum of 8. And I think I'll post up a video on this. The next shell again has another 8. So as you build up your way to calcium, right, element number 20. And then if you keep on going, the number of electrons continuously increases and increases. So I think it goes 2, 8, 8, 18, and so on, right, as we get into the transition metals. So main takeaway from both of these models, the Bohr-Rutherford model is going to show us total number of electrons. Over here, we're just looking at what we call the valence electron. And an easy way to also figure out what valence electrons are incorporated for any one of these elements is go to your periodic table and look at what group these elements belong to. So for example, if we flip back to the P table, so if I go back to my internet, so let me go back to P table. Right, at the top here, these are all our group numbers, right? And we go across from 1 to 18. That second number on the end of the double digits, except we're going to skip over transition metals at the center, is going to tell us what number of valence electrons are available for bonding. So for example, anything in group 1 will have one valence electron. Anything in group 2 has 2 valence electrons. And then as we keep on going, right, skip over these transition elements. Something in group 13, don't worry about the 1. So the 3 tells you that all of these have 3 valence electrons, 4, 5, 6, 7. The exception here is helium. This has 2 valence electrons, but neon and everything underneath neon has 8 valence electrons. And something to keep in mind for this group right here. So if we are looking at these ones here in our noble gases, right? Once we have 8 valence electrons in the outer valence, we say that these electrons form a stable octet. So a stable octet means they have 8 total electrons. And these elements, neon, argon, krypton, xenon, radon, etc., do not want to bond with any more elements on the periodic table. They're happy, they're contented, they don't like to give away electrons, they don't like to share electrons, they don't want any more electrons. We say that they have a stable octet, they have a full valence. They can only take a maximum of 8 electrons, and now they are happy. Okay, so keep that in mind, that these electrons have a stable octet. Helium is the only exception. Okay, helium here has 2 valence electrons, right? Because helium only is element number 2, atomic mass 4. So if you had to figure out what the total number of electrons helium has, and you drew the orbits around the nucleus, then it should make sense that there's no way possible for helium to have 8 electrons. Okay, so just bear that in mind. Now, if you had to draw some Lewis dot structures, let's say we drew a Lewis structure for helium versus a Lewis structure for neon, right? The Lewis structure for helium would be He and 1 dot here at the top and 1 dot here on the side. So we usually go in a clockwise fashion. And the dots represent the 2 electrons in the last orbit outside. And then for neon, same idea. So what I'm going to show you next is comparing the Bohr-Rutherford model for an element versus the Lewis dot structure. So let's just flip back to the whiteboard for one more example, and then we'll wrap up. So again, here's the Bohr-Rutherford model for carbon. Here's our Lewis structures. So I'm just going to zoom out. Let me also erase this annotation from the side, just so we don't get distracted. Okay. And I'm just going to, whoops. Add a new page. Or, okay. So let's move our diagrams a little bit over. So that's our Bohr-Rutherford. That's our Lewis. Maybe let's put them up here, just so we have something to refer to. And let's pick something different and something that should be a bit obvious to us. Let's say that we pick, I don't know, let's pick sodium. So sodium here is atomic number 11 on the periodic table. And we want to draw both the Bohr-Rutherford diagram for sodium, and we also want to draw the Lewis dot structure. So how do we get here? How do we get to Na with just one dot, as what's being shown in this depiction? So let's figure this out. So we already know a little bit of information here. Let's start with the chemical notation. So we're going to write down Na somewhere on the screen. Let me make sure I have enough space. Right, so I'm going to go back here to my periodic table and look up some information for my chemical notation. So sodium, Na, has atomic number 11, and this is a good one to show you how to round up the numbers. We have atomic mass of 22.99. You can round this number up to 23. So it's easy to do the math in your head, and also you can work with the whole numbers, right? Because we're going to need to also figure out the number of neutrons, right? Because we're going to use the number of neutrons to write that down in terms of, putting together our Bohr-Rutherford model. So remember that if we're going to figure out our number of neutrons, we're going to take the atomic mass and subtract from the atomic number. So later we're going to figure out that 23 minus 11 gives us 12. And I'll show you again how to do that. So we're going to need Na, number 11, and 23. So let's go. So chemical notation, we'll keep this side empty for our Bohr-Rutherford model. Sodium is Na, right? Remember, small number at the bottom, larger number on top. So we said that the atomic mass was 23, and the atomic number was 11. So this is sodium. And so this is the element that we are currently practicing. And now we're going to move into our Bohr-Rutherford model. So we need our number of protons and our number of neutrons. Remember, the protons are the same as the atomic number. So if our atomic number is 11, then the number of protons in the nucleus is also going to be 11. So we're going to write that down. So we're going to write 11 protons. And P plus means protons. Protons have a positive charge. And your number of neutrons are going to be 23 subtract 11. So 23 minus 11 is 12. So you're going to have 11P plus, and you're going to have 12 N, and a little circle or degree symbol or a naught. So that tells us the neutrons have 0 charge or no charge. So this is in your nucleus. Now you're going to draw a circle around them. Okay. So that's your nucleus. How many electrons does sodium have? Remember, your number of electrons is also equal to your atomic number, right? And our atomic number here again is 11. So this number 11 is very important. So we're going to now draw the orbits and place all of our electrons on the energy levels. So we're going to draw a few of these circles. Sorry, they're not perfect. They just give you the general idea. Unless we're drawing from a computer screen. Let's just fix that one a bit so we get a little more spacing. Maybe we might need 3 orbits. Who knows? Let's find out. And I will use a different color for my electrons. Perhaps I'll use green. Okay. So total number of electrons are 11. This orbit right here is our first orbit. We are going to put only 2 electrons in this orbit. And hopefully you do a better job than me and draw perfectly nice dots. So these are our 2 electrons, so 11 minus 2. So we have 9 more to go. The second energy shell, you will draw in 8 electrons. So you're going to go clockwise first. 1, 2, 3, 4. Okay. Keep track how many electrons you've added so far. So we have 1, 2, 3, 4, 5, 6. Now we're going to start pairing up the electrons. 7, 8, 9, 10. So now the second energy shell is full. It can only hold 8. And we have 1 more electron left. So the 11th electron will go on this third shell right here. I'm going to draw it slightly larger on purpose. So that's number 11. So we have 11 electrons on all of these orbits. And this is our Bohr-Rutherford model. So I'm just going to call this the BR model. Now, let's move on to the Lewis structure. So where does that dot come from? Remember that the valence electrons are found in the outermost orbital, right? So the last orbit around the nucleus. So that last orbit is right here. And that's the last electron. So when we draw the Lewis dot diagram, or the Lewis structure for sodium, that's the only electron that we're interested in. That's the electron that's going to take place in a chemical bond. And we're just going to draw 1 dot. Now you might be thinking, Miss, does it matter where I draw this dot? Do I have to draw it at the top? Because in the picture it's on the side. Well, no, it doesn't. If you draw it at the top, or if you do this, and you put your dot over here on the right, or if you write it in a different orientation, and you put it over here on the left. Oops. Let's try that again. All right, let's say you write it again, and you put it over here on that side, or even at the bottom. Right? Some people draw, a little dot at the bottom. Any one of these 4 is fine, but according to chemical notation or chemical conventions and most scientists, they prefer going in a clockwise fashion. So therefore, we usually assume this one to be the most correct. This one is a little bit easier to see as per this diagram above, because we can already tell as we go by reading a clock that we start from right and go all the way around to the top. So either one is fine. So I will post up some practice material for you in order to go through drawing Bohr-Rutherford models, the Lewis dot diagrams, practicing a little bit more with the periodic table, subatomic particles and chemical notation, things like that, deciphering chemical symbols, which element is, in a certain period or a certain group, as this many valence electrons or this total number of electrons, things like that, so that you are a little bit more in tune with what I'm looking for. And this will come in handy as we get into chemical bonding. So I hope this tutorial was helpful for you. Sorry for a little bit of the technical glitches along the way as I was trying out this new whiteboard system here. And I will see you in the next video. Take care and happy studying.